Hi, welcome to Pre-Algebra, Lesson 9-7, Simulate Compound Events. So you'll be able to simulate a compound event to approximate its probability. Let's start with solve and discuss it. Jillian lands the beanbag on the board in about half of her attempts in a beanbag toss game. How can she predict the number of times she will get the beanbag in the hole in her next 5 attempts using a coin toss? So you know what beanbag is? Basically, it's a bag that has beans in it. You can toss it for games. So in this situation, if you look at the picture, you see 2 blue beanbags and 1 red beanbag, right? How can she predict the number of times she'll get the beanbag in the hole in her next 5 attempts using a coin toss? So what are we trying to see? What would be all the possible outcomes? And think about the favorable outcome, right? All the possible outcomes of not getting into this hole. Our favorable outcome is to get the beanbag into the hole, right? So yeah, how can you use what you know about the theoretical probability of landing heads up or tails up? So remember how you toss the coin. You'll have heads up or tails up, 50% chance, right? If the coin lands tails up, right? You have a tail, and then if if the coin lands heads up, then you'll have a head. You have 2 different possibilities, right? Here, actually, it looks like there may be more outcomes, but not really. You just have one outcome that goes into the hole. You throw it and it goes into the hole. You throw it and it doesn't. So there are no other outcomes, really. You just throw it, and there are 2 outcomes after you throw, right? If it goes in or if it doesn't. Now it seems like it's harder to toss the bag and get it into the hole, but in terms of outcomes, we only have 2 different outcomes here as well, just like a coin, right? So yeah, if the coin lands heads up, the beanbag will land at the board, for example. We can match it with the coin toss, right? Using a coin toss, right? And if the coin lands tails up, the beanbag will not land on the board. And you can flip the coin 5 times to represent 5 attempts. So let's record that. Let's write that down. If the coin lands heads up, the beanbag will land on the board. If the coin lands tails up, the beanbag will not land on the board. Flip the coin 5 times to represent 5 attempts. Okay, good. So let's look at focus on math practices. When might it be useful to model a scenario with a coin or other tool? When it's easier to use the coin. When is it easier to use the coin or other tool? So in this case, we're using a coin toss because there are 2 different outcomes, and that's very similar to a coin toss. So it might be useful to model a scenario when it's easier to use the coin or other tool to generate results than to actually toss the beanbag like that, right? So sometimes we can replace it with a coin toss or some other simplified tool to represent the scenario, but it should represent the same outcomes, the same possibilities. So let's write that down. It might be useful to model a scenario when it is easier to use the coin or other tool to generate results than to perform the action or record the actual results. Okay. So that was an intro of our lesson. So we are going to look at some tools to or other methods to generate results than to actually perform. So let's start with example 1. The essential question for this lesson is how can you use simulations to determine the probability of events? So we're going to look at simulations. Simulate a probability situation using a spinner. Nikki is planning a hike for the end of the week. She really does not want to hike if it's raining the whole time, but it's okay if it's cloudy. Based on the weather forecast, should she postpone the hike? So look at this forecast, 3-day forecast here. We have Thursday, Friday, Saturday, and they're all raining with a 40% chance. So in order to decide, in order to simulate a probability situation using a spinner, probability situation, we can use a spinner, right? This is one tool. So develop a probability model for rain on a given day. We have a sample space where it's raining or not raining, right? Cloudy is okay, it's still not raining. So list the 2 possible events and their probability. So rain out of the week would be 40% Thursday, Friday, Saturday, right? And then we don't know on which exact day. It just says at the end of the week. Yeah, maybe she could choose a day from here, right? So yeah, there are 2 possibilities, raining or not raining, but we have a 40% chance of rain, so that's given. So that means probability of raining would be 40% or 4/10, and no rain would be all the other percent, which is 60%, right? And so we can design a simulation using a spinner that represents this probability. Raining would be 40%, so we could have 2 out of 5 on our spinners that are rain, and 3 out of 5 would be 60%, right? Without raining. So this is a simulation just to represent our situation and our probability. And then, yeah, it's a model of a real world situation that can be used to find probabilities. The spinner has outcomes and probabilities that match the real world situation with the exact percentage. And so if you run the simulation, we can spin the spinner 3 times, and for each day, Thursday, Friday, Saturday, right? We could record the results. So first trial, we got a rain and no rain and no rain. So we have one day that's raining and all the other days are not raining. And then trial 2, not raining again for 2 days. Trial 3, raining, rain, not rain. Trial 4, not rain, not rain, not rain at all. Trial 5, rain, not rain, not rain. So based on these simulation, Nikki actually should expect raining on one day, one of these 3 days, which means she probably has at least one day that is not raining. So trial 3 gives you one day that's not raining, but then all the others, we have at least 2 days, right? Of not raining. So she could still hike when it's not raining. There is no trial yet that rains for all 3 days that she's possible. So based on the simulation, she probably has a better chance to have at least one day that she can hike. So she shouldn't postpone her hike based on the simulation. Now, is it going to be exactly like this? No, probability is always a prediction. So it gives you a good prediction of a future event, but it doesn't always mean it's going to happen as it is because it's not 100%. We cannot ever be 100% sure that anything's going to happen. But this, based on mathematic probability, is a better choice. Okay, let's look at try it. There is a 50% chance that a volleyball team will win any of its 4 remaining games this year. A spinner with 2 equal sections, number 1, which represents win, and 2, which represents loss, is used to simulate the probability that the team will win exactly 2 of its last 4 games. The results of the simulation are shown below here. And so let's fill in the blank. Pause the video, see if you can fill in the blanks by yourself. Come back when you're ready for answers. Okay, are you ready? Shouldn't be too hard. Out of 10 trials, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 trials, there are how many favorable outcomes? What is our favorable outcome? Winning the game, of course. But here we're looking for the probability that the team will win exactly 2 of the last 4 games. So we want exactly 2 wins, which is exactly 2 ones. So this one is favorable. That one is too many wins. This one favorable, no, favorable, not favorable, not favorable, not favorable. So we have 4 favorable outcomes out of these 10 trials. Based on the simulation, the probability that the team will win exactly 2 of its last 4 games would be 4 out of 10, which is 0.4, which is 40%. Okay, so convince me, does the probability that the team will win 2 games change when exactly is replaced with at least? So it's instead of exactly 2, winning exactly 2, if we say at least 2, so that means 2 games of winning, 2 games out of 4 winning, or 3 or 4, right? Then it would, of course, change because on top of all of these 4 favorable outcomes, we can also have this and that and that, right? So we have total of 1, 2, 3, 4, 5, 6, 7 favorable outcomes. So yes, it will change. There are an additional 3 favorable outcomes. So based on the simulation, the probability that the team will win at least 2 of its last 4 games is 7/10 or 0.7 or 70%. So 70% is a lot higher than 40%. So it will more likely be true. Okay, let's look at example 2. Simulate a probability situation using a coin. So the Hornets and the Tigers will play a 5-game series with the winner of 3 games named the state volleyball champion. The 2 teams are evenly matched. Use a simulation to find the probability that the Hornets will win the 5-game series. So there are 2 different outcomes, right? 2 possible outcomes, winning or not winning, right? So we can use the coin. Because the probability model, the sample space, would be whether the Hornets win or the Tigers win, right? So we can list the events and probabilities using that. So the probability that the Hornets win would be 50%. Probability that the Tigers win would also be 50%. So if it's 50-50, we can use a coin. Coin is a great example for that. So design a simulation using a coin. The outcomes and probabilities of flipping a coin can be matched with those of the game. So we can run the simulation when we decide that heads would be one and tails would represent another outcome, right? So heads would be for hornets, tails would be for tigers. The acronyms match, so that's easy. So run the simulation, you flip the coin and run the trial. So trial 1, we have 5 games where 3 times we have heads, which represents the hornets would win, right? So 3 out of 2, that means hornets win by 3 out of 2. The tigers win trial 2, 3 out of 2. Trial 3, the hornets win 3 out of 2 as well. Trial 4, tigers. Trial 5, hornets. Trial 6, hornets. Trial 7, tigers. So find the probability. So we're not counting the whole H and T here. We're looking at the outcomes for each trials. So from these trials, out of 7 trials, we have the hornets winning 1, 2, 3, 4 times out of 7. So the hornets have a better chance of winning according to our simulation, but we know it's going to be 50-50% chance in real life, right? So we really don't know. Okay, example 3, simulate a probability situation with a random number generator. So another tool is a random number generator. When we represent different outcomes using numbers, then we can use a random number generator. So let's look at this example. An energy bar company is printing equal quantities of 6 different collectible cards. The company will randomly package 1 card inside the wrapper for each energy bar. Ooh, what's the probability that all 6 collectible cards will be packaged in a box of 10 energy bars? So have you ever had this type of experience as a kid? Trying to get that 1 card out of a snack box or cereal box. You know, there are different things that you might favor that they hid, or maybe sometimes there are like tickets for something or winning a prize. You see a lot of events going on from these companies. It's marketing because not everyone will receive it, but somebody may. It's like a lottery, right? So here we have 6 collectible cards, and they'll be packaged in a box of 6 different collectible cards, and we have 10 energy bars. We're gonna buy 10 energy bars, but we're gonna simulate it first, right? So use a random number generator to simulate the situation. So we can say numbers 1 through 6 represent each of the trading cards because we have 6 different collectible cards, right? So and then each trial has 10 numbers. We have numbers 1 through 10, but then numbers 1 through 6 represent the cards, and then 1 through 10 would just be representing our sample space, buying these energy bars, and some of the bars don't even have any cards, right? So trial 1, we use the run the number generator and generate all these numbers. We have 4, 4, 6, 3, 5, 6, 1, 6, 6, 1, and we have 1, 3, 4, 5, 6. We don't have 2. And so it's not a full set of cards. And then trial 2, you do it again, not a full set of cards, full set of cards, dot, 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 dot. So the probability that all 6 collectible cards will be packaged in a box of 10 energy bars is pretty low. 1 out of 8 trials would give you a full set of cards. So based on 8 trials of the simulation, the probability, probability is 1 out of 10, 1 out of 8, or 12.5%, which is pretty low. Okay, let's look at try it. In a tennis tournament, 25% of Sarah's serves were aces. Design a simulation to predict how many aces you expect Sarah to serve out of 50 serves. So pause the video and think about what would represent your situation best using a tool, and simulate it, design a simulation, and then predict. Okay, are you ready? if you're ready for the video, if you're ready for answers, then you can play this video again. So here we have 25%. What type of simulation or tool, simulation tool could we use to represent 25%? Definitely not a coin. Coin is only for 50% chance. As we looked, number generator would also be a possibility. But as we looked at it in example 1, spinner, right? Spinner would also be another good one. So if we use a 4-section spinner, then we have 25% for each, right? Yeah. And then we could spin it, and then design a, and then simulate it, right? And then, yeah, and then you can decide how many times you're gonna simulate it, and then yeah, and then find out the results. So you don't actually have to simulate it, you just design a simulation. So one method is using a spinner. Another method, you could also use a random number generator, but you have to set the numbers only from 1 to 4, and then you can represent number 1 to be aces. So you need to make sure that your sample space matches, and then you have a number that represents. Okay, so I'm gonna write both of them. So number 1, spinner. Use a 4-section spinner and select one section to represent serving an ace. Spin the spinner. Let's say 50 times, because it's easy to serve, right? And record the results. And then the next one, we can use random number generator. Use a random number generator to randomly generate a number that represents serving an ace. The numbers should be from 1 to 4. Generate numbers 50 times and record the results, right? So those would be 2 different ways. Obviously, you can be creative and think of other ways, but these are the examples of the tools that we used in this lesson. And this would be able to cover pretty much all the different scenarios that we'll see in this class. So let's summarize our lesson. Key concept on the next page summarizes your lesson very well. A simulation is a model of real-world situation that can be used to predict results or outcomes when the actual event is difficult to perform or record. A simulation uses a tool such as spinner, number cube, coin, or random number generator. Oh yeah, we could use a dice too, for which outcomes have the same probabilities as the actual event. So a greater number of trials would usually get results that are closer to the theoretical probability of the actual event. So it may be more trustworthy, but again, your actual event is really unpredictable. Like you can never be 100% sure of an outcome. So there's always some probability that it's not going to go as we predicted, but there is a better prediction than others. So this was lesson 9-7, simulate compound events. And this should be the last lesson of this topic. We'll continue with these lesson videos in the next topic. See you later. Bye.